I know it's been a while. I know you might not have done any stats for roughly a week or so. And just remind you guys, as you just came in, the quiz on Thursday, chapter 4 and 5. This is chapter 6, so this will not be on the quiz. Okay, so let's remember how to use this chart. And I also want to so sometimes when you start using a chart or you start using the calculator to get some numbers, you sort of lose touch with the idea behind it. So let's just remember some things about this distribution. Can anyone tell me, for a normal curve, this is a normal curve, what percent is below the mean? What do you guys think? So if you have a normal distribution, what does the mean kind of do to it? Chop it. Cut it in half. So what percentage would be below the average? 50%. Kick ass, right? So, and can somebody remind me, what does the z-score tell you? Remember, this is kind of funny to me because as a student, what is the one thing you definitely want to know about the next test? Don't you want to know what I'm going to ask you? Wouldn't that be great if I just told you what I was going to ask you? Yeah. Yeah. So I told you I am going to ask you a question on every test left this semester. I told you what it is and I told you what the answer is. So can anybody tell me what a z-score tells you?
A standard deviation away from the mean.
How many standard deviations? So I really want this to make a ton of sense. So standard deviation is sort of related to inches versus millimeters versus feet. So if my distribution is really spread out, I might want my standard deviation to be really big so I can kind of step around it pretty well. If my distribution is really skinny, I want my standard deviation to be small. So it's sort of like measuring something in millimeters versus measuring it in miles, right? A z-score is when I put that ruler down and see how many steps away things are, like 3 inches away or 7 feet away or 18 miles away. So all a z-score tells you is the number of standard deviations from the mean to the data point. Don't memorize word for word. Do you understand the idea? All a z-score is a distance. If you just say distance, not good enough. If you just say distance from the mean to a data point, not good enough, because I'm going to be a dork and I'm going to write in miles, in light years. So the units isn't miles, it isn't inches, it isn't centimeters, it's standard deviations. How many standard deviations away? And I want this to really make sense. So the mean, if the z-score tells you the number of standard deviations from the mean to the point I'm talking about, what would the z-score for the mean be? How far is the mean away from itself? 0. Right? So whatever the mean is, its z-score will be 0. So if I go 1 step down and 1 step up, somebody remind me, we've done this one enough, what percentage would be in here? 68%. So again, if I have a distribution that is really, really, really skinny, it's still normal, the standard deviation will be much smaller, right? This one is this big, this one is this big. You guys with me? Standard deviation, of course, will be smaller because the standard deviation is this measure of how spread out the distribution is. So do you see how I'm still going to catch 68% because there's more stuff squished in there? So no matter what my distribution kind of looks like, as long as it's normal, it could be a fat one, it could be a skinny one, go 1 step up, 1 step down, 68%. Maybe. about 2 steps out? How much is in there? 95. Become a 5. So here, 2 steps out, 95%. I really desperately want this because I always try to show you the physical analog to what the hell we're talking about. So if I have a really skinny distribution, I want to take little frickin' steps to kind of walk around it. So that's my standard deviation is really tiny. If I have this frickin' huge, I want my standard deviation to be huge so I can get the freak through it. So that means as it gets skinny, everything gets smushed to the middle. 1 step out still catches 68%. If it's really spread out, 1 step is huge, but it still catches 68% because now it's spread out. Okay, maybe. So help me out here. What percentage is here? What percentage is in this little piece? Beautiful. If there's 95% in here, there's 5% out there, right? If there's 95% in, there's 5% out, 2.5% on that side, right? So this would be 0.025. So, everybody, let's look at our z-score charts. Let me know if you need one of these little blue dudes. If I want to verify this area, this probability, what do I look up on the z-score chart? Am I on the correct side? I want to go negative. I love it. They go positive, we go negative. All right. And then negative, and so here's the big thing about this chart. Once you see how to read it, you should be good. The way they've set it up is I'll look at negative 2.00. So 0.0228. So the actual is 0.0228. So when we do the empirical rule to make it easy to remember, we kind of rounded this number. So it's roughly 2.5 when it's actually 0.0228. So what this chart does is it gets a lot more specific than the empirical rule, right? A lot more specific, and it rounds a lot less. It goes out to 4 places. Right? So that's pretty close. The 2.5%. It's pretty close. The reason it's not exactly right is because we rounded this number to make it easy to remember. Okay, maybe. All right, so again, with the uniform curves, we saw that the area of the part that's related to the question is the probability. Just like throwing a dart, the freaking little bullseye is so tiny, that's why it's got such a low percentage chance of you getting it. So if I get it several times in a row, that is compelling evidence that I can throw that damn dart really well. Because it's really unlikely I would do that if I just randomly throw it, right? I must know what the hell I'm doing. And obviously you can tell I don't. But so let's look at this. Turn this sucker around. And again, let me know if you need this handout. It's the one that on one side was the uniform distribution and the binomial practice. Right, it had the take a quiz question. Okay. So last time we got this one done. You guys just verify real quick. Can you look up 1.18 for me on that blue chart? Make sure you can get that 8810. Let me know if you can't.
I can.
So 1 point, so watch this, a little bit weird. Go to 1.1.
1.1?
Yep.
Right.
And then you see how the next digit is 8.
Oh.
So then if you go.
Oh, like that? Oh,
Yep.
Thank
Got
you.
it. Okay. So they try to make it so it all fit on one sheet. So to do that, we have to realize how the hell to read this thing. So the first decimal place is here. And then the second decimal place is up here. So 1.18, 0.8810. Which means, if you did a test in a class and the grades were normally distributed and your Z-score was 1.18, you would have scored better than 88.1% of the other students. So somebody said something about percentiles last time. I don't think it was quite the answer I was looking for, but you can see how this is related to percentiles. This is like a giant thing of percentiles for a normal curve. That's what this chart is. Right? Remember, what's a percentile? The percentage that's below that score, right? And that's exactly what this tells you. In fact, the freaking picture at the top tells you, when you look up a Z-score on this, it's going to tell you the area below it, which means the probability of getting something below it. So something I didn't say, and I don't think I've ever said this, but I think you guys really understand the dartboard thing we talked about, right? The little tiny bullseyes with tiny, it's got a little tiny area. So its area is directly related to its probability of you just getting it by randomly throwing the dart. I gotta stop throwing the dart. So if I had this up on the wall and people just randomly threw darts, right? What's the percentage of them that would land in the shaded area? Well, if it's 1.18, it would be 88.1% would land in that area. Maybe. Okay. So, there's always two levels to any statistical idea we talk about. There's the concept of it, and then there's a freaking nuts and bolts part. Looking stuff up at the table, using the right formula, right? So can you guys take a minute and try to do part B? And I highly recommend. I don't take points off if you don't draw the picture, but if you make a mistake and get the wrong answer, I take more points off because I don't know what went wrong. So I highly recommend you draw the picture, you put the Z-score down, and you shade in the area I want, right? So what's always right in the middle of a standard normal distribution? What's always right in the middle? Zero. So make sure you put negative 0.52 in the right place. Yes?
So is that a zero right there? Negative? Is that a negative zero?
Yeah, negative 0.52.
Okay, negative.
Yeah. So like half a step down.
Okay.
Yeah.
I see.
Catch up with you guys. So negative 0.52, where would that be? To the left. And then what's the area I'm asking for? Where would you shade? Greater than, sure.
Mm-hmm.
Which is which side? On the right, I love it. So, can anyone tell me right now, before you even look it up, is it going to be less or more than 50%? More. How do you know that? Some of you guys are like, how the shit did you know? Well, again, above zero would be what percent? Because the mean cuts it in half. So of course, this should be more than 50%. So the picture should help you make sense if your answer seems right. It should be bigger than freaking 0.5.
Question.
Yes.
So for the A and B one, so for A, when you look at the sign, you're going negative, but for B, the sign, you're going positive. So is it like opposite kind of in a way? That makes any sense?
Well, yeah, part A and B are opposite kind of questions.
Yeah.
Yes.
But I'm saying like the equation, so whatever the equation is, the graph would be opposite of it.
Oh, I see. Here's the really cool thing. All right, inequality, students sometimes have some trouble with them. I always remember less than is the one that looks like an L that's kind of fallen over. But here's the beautiful thing. It's a little arrow that points you in the direction you're supposed to shade.
Okay,
you see
that's what I
that?
was thinking.
Do you see that? So the little arrow, it's just a little arrow. So that one is an arrow pointing that way. I want to shade up. So can everybody look up negative 0.52? Has anybody looked that up yet?
I did. And
Yeah.
I did like what you taught me.
Negative 0.52?
And I got this number right here. 0.30.
All right, cool. Yeah. So here. So negative 0.52. Negative, Jeff. You got it. Negative 0.52. So I get 3015. And here, really quick. This is really sucky. This is not negative 0.51. This is negative 0.50. 1, 2, right? Does everybody see that, the 0.3015? Where is that on the chart? Is that the answer?
I think so.
What does this chart always tell you? What does this table always tell you? Areas that are below. So this is 0.35, whatever the hell it was.
3015.
3015? Thank you. Does that answer the question then?
No.
No, so this is exactly the same situation as if it was a 30% chance of rain, what's it probably a not rain? So if this side is 0.3015, what's this side gotta be?
6985.
Yeah, 1 minus that. You guys see that? The whole picture is 1. So if one chunk is 0.3015, the other chunk is 1 minus 0.3015.
So it's always 100%.
The whole picture has to be 100%
Okay.
in order for little chunks to be probabilities. You guys follow what's happening? So this is sort of funny because the chart sometimes gives us the opposite answer. So then we do 1 minus, like the same way we do any opposite probability. You guys kind of follow? So if they ask me a question, the probability is too hard, I do the opposite and then do 1 minus that. So it's basically what we're doing. So what, did I show you the shortcut to, and I know the ultimate shortcut is just throw in your calculator, but did I show the shortcut for subtracting? I think I did. What makes 3, 9? 6. What makes 0, 9? 9. What makes 1, 9?
8.
What makes 5, 10? So if you make everything 9, except for the last one, make it 10, that's the answer, the little shortcut. Or you just put it in the old calculator, right? Now, let me see. So again, if you took a test and it was normally distributed the grades, and your z-score was 0.52, right? Negative 0.52, so you're half a step down roughly from the mean. That means that's almost 70% of everybody else scored better than you. Is everybody with me? Real quick, everybody look at your z-score chart. Look up positive 0.52. What do you get for the answer? Don't say anything. I want everybody to see it themselves. Positive 0.52. What answer did you get for positive 0.52?
It's the same thing like we got right there.
This freaking thing. So, the picture is symmetric, yes? That's one of the fundamental things about normal distributions. It's symmetric. So the amount above negative 0.52 is the same as the amount below positive 0.52. So if you don't understand anything I just said within the last 30 seconds, don't worry about it. We got the answer already. But that's a little tiny shortcut. A little tiny shortcut. And it's because it's symmetric. You can actually look at the positive one in some situations. Okay. Maybe. All right. I'm going to let you guys, can you draw part C? And then I'm going to give you a minute or so to try to figure out how to do it. This is, part C is a little bit rougher because I got 2 freaking z-scores, right? So first draw it. Shade in the area that it wants. Catch up to you a little bit. You always put 0 down there. Now, your chart can't handle this. right? You can't look up one thing and be done with it. So it's a very physical interpretation to what to do in this situation. If I look, can everybody look up 1.49 for me on your z-score chart? If you haven't done it yet, look up 1.49.
I got it.
Yeah.
It says, 0.9319.
Okay.
I don't know if I'm correct.
Yeah, let's see. 1.49. 9319, yes. So wouldn't that be this entire area? It's everything below it, right? You guys, anytime you look up a z-score on the chart, it tells you the entire area below what you just looked up, right? That's what the chart does. It's a very single-minded chart. That's why it's only one side, well, a two-sided one page. Is this more or less than what the actual answer is supposed to be? Does everybody agree? That's definitely more than I wanted, isn't it? How much more is it? I only want this area, and I got everything. So how much is it too much by? What? Yeah, doesn't it include this shit too? Do I want to include this? No, I will. So if you look at 1.49, it includes all the area, all the way, everything forever down. But I want it to stop here. So let me just look up the area below this, and then I can subtract. Right?
I did look up that.
Okay,
area.
what do you get for negative 263?
0043.
Sounds about right. 263, 0043. Well, I'm pointing the wrong thing there. 263, yeah. 0043, 11. So that's here. You guys get the physical nature of that. I've included too much in that first one. I just got to subtract the area from the second dude. And that'll be the area in between. So whatever the hell 9319 minus 0.0043 is 9276. Maybe? I like it. This is the work that I really kind of need to see happening. Okay, so let me ask you guys something about this to lead into the next question. When we looked up negative 0.52, we got this, right? This is basically the percentage below that. So this would be the percentile for this. Percentiles are the area, or the probability, the percentage that's below a given score. So look at the next question. I don't know the z-score for the next question, but I know the area that's somewhere, right? Where would the z-score be? It's got an area of what, where? The z-score that has an area of how much? 38% below. So where would it be? So put 0 right in the middle. Is it going to be to the left or the right of 0? It's only supposed to have 38% below it, and 0 cuts the damn thing in half. So it can't be here, obviously, because that would be 50% below it. So is it over to the right, or is it down to the left? Which one? Yeah, because it's only supposed to have 38%. So if I start at 0, there's half of it below. Is everybody with me? If I start moving this way, don't I have less and less area below as I move? So I want to kind of put it, and again, this is just a visual aid. You don't have to be perfect. So somewhere right here, this is 0.38. I really want this to make sense. So the chart translates between z-score and probability. If they give me a z-score, I can look up the probability. If they give me a probability, I can then look it up in the middle and see what the z-score is. I have to do everything in reverse. The really evil thing is 0.38 looks like a z-score, right? So if you look at 0.38, you are not doing the right thing, but I kind of can't blame you because 0.38 looks like a freaking z-score. So I don't know the z-score, right? Where in the table are the probabilities? Where are the areas?
Center.
In the middle, in the body, right? Is this going to be a negative or a positive z-score answer?
Negative.
Because it's below the mean. So negative z-scores. Don't look up 0.38. No. I want to find 0.38 in here, or the closest I can get. So don't say anything.
I found it.
Okay, hold on to it. I want everybody to have a chance to try to find it. Get as close as you can get to 0.3800. This is where things get slightly interesting. Does everybody see where there's a 0.38, 0.37 stuff? So it's going to be down here, right? 0.34, 0.37. There's 0.38. But which one of these is closer to 0.38?
37, because it's 17.
Yeah, beautiful. Do you see how this is 21 away, and this one is 17 away? So when I took stats, we had to interpolate. We had to create a linear approximation between these. Oh, screw it, just take the closest one. So what's the closest one? This one. What z-score is this? Negative 0.31. Yes? Okay. Okay, I'm not sure if you really, so if I'm given a z-score, it kind of makes sense that, all right, the mean cuts it in half, and as I move away from that mean, I get more or less area. So the z-score tells me how far from the mean I've moved. So this chart only makes sense that it exists. Depending on where I am, I should be able to figure out how much area is below me. I've moved away from the mean, how much area do I now have below me? So it'll do it both ways. Math very often can go both ways. Right? Just be jealous. If I have an area, I can look up a z-score. If I have a z-score, I can look up an area. So it can translate it both directions. So you guys do part E. Oh, wait.
Let's say that interpolating it or whatever.
Yeah.
I've never tried to do that like linearly, so I was just like, like what's in the hell? I'm just kind of like eyeballing it.
Yeah. So I do accept if you said like something like negative 0.305, because it is almost roughly exactly between the two.
Yeah.
Yeah. So I mean that's a better answer, a better approximation. But then you can actually set up.
Yeah, because you said when you had to put like a linear thing between the two, I was like, it's not linear, is it? Because
It's not linear.
Yeah.
It's just an interpolation between the 2 points. But you're right, it's not linear. So even that's not.
Yeah.
That's why it's like, well, if you try and improve it, you still don't do it very well. So you might as well take the
You need to
closest
do
one.
algebra.
Yeah, it's either, in fact, if you get to that point, then you're like, just use technology.
Yeah.
Right?
Alright, fair enough.
And I am going to show you how to do some of this in the calculator, but I think you probably know me by now. You don't just tell me what buttons you pushed. That's not showing work. So there's several things happening here. The middle is 0 because it's a standard normal curve. So it's talking about z-scores. This is supposed to have 10% above it. So does it make immediate sense where it's got to be? Could the z-score be here? How much would it have above it? More than half. You guys with me? Because the mean has half of it above it. So the z-score can't be down here because then it's got more than half above it. So where does the z-score that would be the answer to this question, where must it be?
Alright.
It's got to be way the hell up here. So it's only got a little 10% above it. Maybe. So the picture should help you. So if you don't draw it correctly, you're going to totally destroy it. So the minute I figure that out, so it's roughly about right here, this is 0.1. So will the answer be a positive or a negative z-score?
Positive.
Yeah, so the minute you draw the picture, you know what side of the chart to look at. Are you going to look up 0.10 though? This chart is stupid. This chart only understands one thing: the areas that are below a z-score. Is that area below a z-score? Nope. So if there's 10% here, there must be 90% below it. So in order to use a chart, you need two things. You need to have a normal curve. This chart does not work unless I know it's normally distributed. Okay, that's number one. And the picture at the top of the chart keeps that. I can't erase that shit. So you've got that as a note. Only use this if it's normal, right? And secondly, I forgot the second thing already. It took too long. Oh, you need areas that are below the z-score. So let's look at 0.9. Can you guys find the closest you can get to 0.9? It should be something, yes, it should be something interesting. Maybe? I can't remember. Okay, let's see. Well, 0.95 would be interesting. So what's 0.9? What's the closer you get to 0.9? Yeah, this one's pretty straightforward. There's an actual closest thing you can do, right? So let's see. 0.6, 0.7, 0.8, 0.9. Okay, so here's 0.9. The closest I get to 0.9 is with one of these, and obviously it would be this one. This is only 3 away. This one's 15 away. So what z-score is this? Oh shit, I have no idea.
1.2.
1.28. So again, if I said somebody's in the top 10% of the class, their z-score should definitely be positive. They are above average. And it's a decent, it's more than one step up. If you're in the top 10%, you're more than one step up above the mean. That makes sense. So we got 1.28. That makes physical sense. Okay, so now before we do this next part, we got to remember a few things. Hey. So let me make clear something that was up there. If I say we have a standard normal distribution, that means everything is already, oh, I thought it was my camera. Everything's already z-scores. That's what it means. Everything's already z-scores. So this would have 0 in the middle. Any numbers here would represent a z-score. Is everybody with me? So that's what standard normal means. If I standardize something, I'm converting it to be the same amongst everything of that same shape. So that's what z-scores do. So real quick, little side note. But let's do this. So it's not standard, but it is normal. So if I had, for example, test grades that were normal, and the mean was 74, and the standard deviation is 11, let's say. So I can draw that picture. Thankfully, there's not a 0 in the middle, because these are actual raw scores. These are test scores. These aren't just z-scores. Right? If 0 was the average test score, what the shit? How did people get negatives? Did they hit me with their car on purpose? That would be one way to get a negative score. Okay. So here, what goes in the middle of this picture? What goes in the middle? Not 0. 74, that's the mean. It's not z-scores, it's not a standard. The mean is 74. And let's say I want to know the probability that I get a score above an 80. Where would 80 be on on that picture?
A little under half step above.
Yeah, up from this, somewhere over here, right, of course. I always get people that don't realize this has gotta be a scale, and they just sort of throw 80 wherever they want it to be. So should the probability that I score above an 80, should it be more or less than 50%? Less. It should be a decent amount less than 50%, because it's not even half of the picture. Do you guys see? So your picture, the distribution you draw should help you. If you get an answer of 0.7, you are wrong, and the picture says you're wrong. You can't get 70% of the whole thing just in that little area. What the shit? You can't do that. Now, can I look 80 up on the chart? Why does that not make any sense? This is a normal curve, right? This is normal, so I can use the chart. Do you look up 80 on the chart?
No.
No, because what do you need to use a chart?
Percentage.
Z-scores. It's called the Z-score chart, right? So I gotta have Z-scores. Anybody remember how to change a data point into a Z-score? Anybody remember that formula?
Absolutely not.
So think about it. It's the number of standard deviations that fit between the mean and the data point.
So it'd be.
So I gotta know how far apart the data point and the mean are to see it. And then I wanna see how many steps fit into that.
Divided by the standard deviations.
Yeah. So I'm either gonna give you questions that, see how these questions involve a Z-score? That means when you draw the picture, you can put a 0 in the middle because everything is already Z-scores. This problem, number 2, involves actual raw scores. These are not Z-scores yet. So in this problem here, what would the Z-score for 80 be? How would I set that up? What's the mean? 74. What's the standard deviation? 11. And what's the data point that I'm interested in? 80.
6 over 11.
Point 545454. I don't know either.
Check. Well, like 54554.
Okay.
5.
I like, so 0.5 what? So of course, do you guys understand why I round Z-scores to 2 places? Because the chart only goes out 2 places.
Yeah.
That makes so much sense. Everything else we round to at least 4 places just to stay safe, right? Z-scores, the chart only understands up to 2, so we just round to 2. Will technology be more accurate then? Shit, yeah, because they don't round. Do I care? No. I don't want us pushing buttons and going, I got a number. So there's a method to why I make us do it by hand, and if you don't like it, yeah. So I always have at least one person say, my last stats teacher just let us use the button. No, I don't care what they did. You got me now. Okay. So what would this be? 0.5? 5. Good. So you got to round to the second place. So look what just to keep myself straight here, I always put underneath this, I put in parentheses what the Z-score is. So then it looks a little more like our first pictures we had up there. So if you look up 0.55, don't say anything, just look up 0.55 real quick. See what area you get. If you want to, you can realize what the shortcut would be here, but it doesn't really, it saves you like 1.5 seconds. So 0.55, what area do you guys get? All right, we're all gonna wait for me, okay. I get 7088. So of course, what's the right answer then?
Is that 29 foot?
Yeah, 0.2912. So just under 38% chance. So what that means physically, if this is true, and by the way, I would say it isn't, I just made that shit up. But if this was true, if it did take people 33.74 minutes per week to find a parking spot, right? If that was the actual average amount of time, how much time does it take you guys? Well, you get here pretty early, so like for this class, there's like parking all over the damn place, right?
Yeah.
And in fact, to be really honest, we used to have 20,000 students, and now we have 12,000. So in general, it should be easier. So this data probably isn't true anymore. But back in the day, it sucked. My university sold 2.5 parking permits per spot. You guys understand? So if there was a time of day when more people were there, you were just screwed, right? Anyway, so if this was true, then I could figure out the probability that a student takes less than 27.2, that probably somebody's lucky. It takes them a lot less time to find a parking spot, right? So what I want you to do, try and do 2A. It's exactly like what we just did, except of course the mean and the standard deviation are different. Yes?
Unrelated to math. I don't even think we have parking permits right now.
Oh, you're right, you're right. Right now, I think they're still,
Yeah,
Being
they're
lenient.
charging for parking.
Yeah.
Because like when I get here in the morning, the entire like second floor of the parking garage is empty.
exactly. So, yeah. So, I don't know if we're gonna recover from our enrollment losses. We'll see.
Was it because of COVID or was it before that?
It's, well, I won't get too much into it, but we had trouble before COVID came along, and then COVID gave the administration a nice excuse, right? So if any administrators are watching, hey.
Real subtle.
Yeah, it was kind of funny. We had discussions before the pandemic happened about the fiscal cliff and all this stuff, and then all of a sudden the pandemic happened. They're like, oh, it was the pandemic. God. All right, I'll stop. Try to do 2A. It's exactly like the one we just did. Do you have the worksheet? Okay. Let me see. Is Ty out there? Ty? Davis is out. Oh, sorry. I have like 3 people whose names are at least UI. Yeah. Yeah, Ty, you're Tyrone. Right? Yeah.
This is really, really unrelated, but we were talking about how like this is not about math.
Okay.
We were talking about like how stars are open this. You know, the population of Ireland is still not recovered from the famine. It's still like 70% of what it was.
I mean, so yeah, you look at it's easier for the U.S. to sort of absorb, and we got to realize I don't remember, it's millions of people.
Yeah.
But you have these tiny island countries, little tiny countries, and it's noticeable, hugely noticeable. Yeah.
And then on a much less important scale, my work was talking about, it's like, yeah, like, oh, we used to have like 20 people on this one spot, and now we have like 7 because of COVID.
Yeah. Yeah. We used to have 60 adjunct instructors in math.
And right now?
We have 3. Yeah. And that's not just because of the pandemic, it's for other things, but that's partially because of the pandemic. So just make sure we're all cool with what's happening. What goes right in the middle of this picture?
33.
Yeah, 33.74. It's always the mean right in the middle, right? Which makes sense. It's the measure of the center. And then you figure out where that goes, and then you have to make z-scores. So the main difference between the first set of problems and the second set of problems on the sheet is the first set is already z-scores. You don't have to do the formula at all. Second set, they're not z-scores yet. All right, I'm going to catch up to you on this one here. So see from the picture, it should be a relatively small percentage. It's at least less than half. I know for sure it's less than 50%. So I'm gonna first create a z-score out of this data point. So my data point minus the mean divided by, wow, Jeff, if you could write, everything would be so much better. Okay. Divided by the standard deviation. Oh, if you need a bar calculator, I have some up here. Let's see, what do you guys get for this? So here's a real quick tip. I'm gonna do the work and I'm gonna make a mistake.
Oh my god.
Oh my god. 2 mistakes.
Oh my god, you sound
I
like
made
that.
3 mistakes. Okay. So I pretty reliably have somebody that does this. So the z-score is supposedly 23.29. So at this point, this might not be as internalized. Can anybody remind me? All right, so within 1 step, there's 68%, right? Within 2 steps, 2 z-scores up and down, there's 95%. Within 3, does anyone remember that number? It's a little bit. 99.7. So what that means, if I go 3 steps up and down, I am freaking close to 100% of everybody. If I get an answer like a z-score of 23, do you understand how far away that is? That is the equivalent of like a 40-foot person. Somebody with a z-score of 23, I could calculate it, but it's like somebody who's 40 feet tall. I don't think that should be the answer. It's not impossible that's the no. Can anyone tell me mathematically what I did wrong?
Mathematically, order of operations is wrong.
Order of operations. This calculator understands order of operations. What's the only thing I'm dividing by 8.63? That.
And you're subtracting that from.
So the calculator doesn't have eyeballs, thank God. No, the TI 1000 will, and then that's Skynet and all this kind of shit. So I need to tell the poor little calculator what the top is, put it in parentheses, and maybe type the whole thing in there. So there's the top, divided by 8.63. So you should get negative 0.76. And that makes sense in 2 ways. It's definitely not that far away, and it's definitely negative. It should be a negative z-score, right? Because I'm below the mean. Okay. So this is negative 0.76. This is negative 0.76, and the mean is always 0. So now you just got to look up negative 0.76, and you're done. So this chart that I gave you, this is a chart of answers, right? This is a table of all the freaking answers. And what you need to know before you can use it is it normal, and do I have z-scores, right? To be able to use this thing. So what do you guys get if you look up negative 0.76?
22, 36.
Oh, okay, so 0.76, 0.22, let's say 3.6. And thankfully in this problem, that's the answer. So be really careful, don't just start subtracting everything from 1. What's the only time I'm gonna have to subtract from 1 is if it is the opposite, if it's above the z-score, right? Because the z-score chart just tells me below immediately. So this question was below, done. I don't have to do anything to that. So there's a 22% chance roughly that it would take a gross 1 student 27.2 minutes total for a week to find a parking spot, right? So it's like 5 point something minutes per day on average. Do you understand the physical interpretation of what this is saying? Okay. You guys try to do number 2. I think a few of you guys have already done it. Just, if you haven't done it, do it. from the picture, you should feel pretty confident this is gonna be a pretty tiny answer. So it would be our data point minus the mean divided by the standard deviation. And what do you guys get for that? Anybody get that? Z-score?
98, wait,
Z-score.
2.23.
I love it. And why does that make sense? The standard deviation is 8.6, so double that is about 17 units, a little more than 16. You guys with me? And this is about 20 up. This is almost 20 up, right? So it's going to take more than 2 steps to get from here to there. This is 20 away. 2 steps would be 16, 17. So it's going to take more than 2 steps to get from here to there. So 2.23 makes sense. You always have a physical interpretation what the hell you're doing, which is not true for every math class you've ever taken. But statistics, very often you have this physical idea you can use. So now, don't just circle this, because we're only halfway done. What do you get when you look up 2.23?
Yeah, 9871.
9871?
9871.
9871, okay. So then what's the actual answer? 0129. How to get 0129? Just did 1 minus 0.9871. And again, just to remind you guys, this is the last time I'll do this. If you look up negative 2.23, what do you get?
That. 0.01.
Right? Same thing, okay. And again, if you don't understand that shortcut, never use it. Right? Never use it if you don't understand it, yeah.
Would you subtract? You said subtract what?
Oh yeah, so the whole picture's gotta represent all probabilities, right? So how much should the whole picture be? 1, 100%. So if this side is 0.9871, this side must be 1 minus that. It must be the rest. I love it. Kick ass. All right. Why is number 3 sort of suck? Why is this a math teacher's favorite kind of problem? Because
It's 2 problems.
it's 2 problems in 1. Love it. Being efficient. Be efficient. So this number 3 is pretty much exactly like part C up here, except it's worse because you have to actually make both of these into z-scores. So what goes in the middle again? 33.74. The mean always goes in the middle. And I want 15.5 and 29.5. Good Lord, John. So I gotta make z-scores out of both of those. So then we can do like we did in part C up above. So z-score, making something that z-score is relatively straightforward. Just throw it in the old formula. So I gotta do this. I've gotta do this. So see, 15.5 minus 33.74 divided by 8.63. Shabam. And then I can just do second enter over here and make this 29.5. Shabam. So I get negative 2.11 and negative 0.49. So now I've got to figure out, if I look up negative 0.49, I look up negative 2.11, I have to subtract those areas to get the area in the middle. It makes physical sense, which is neat. So if I look at negative 0.49, I'll get the area that's too much. And if I chop off this much area, so I can look up negative 2.11, I got the area that's between the two. That makes a lot of physical sense. So somebody look at negative, this poor little thing, negative 0.49 is what that's trying to say.
What?
Yeah. It looks like negative point H, but oh well. It does look like a 4.9 there. Yay!
3121.
3121?
Yeah.
So double check, make sure you can find that. Somebody else tell me if you look up negative 2.11. Where you got?
Okay, 0174.
0174. And then you just have to subtract those two, right? It's just kind of nice. If you give yourself that picture, it becomes a more physical problem.
Point 2947.
2937?
47.
47. Yeah, let me talk about something related to this question. This is just like part D above, right? Exactly like, because it's the 14th percentile, but now I want to find the time that represents the 14th percentile. So you guys, take a minute, can you figure out the z-score that's the 14th percentile? Why would the 14th percentile be?
Below?
It's got to be below the mean, because the mean has 50%, I want 14% below it, so it's got to be down here somewhere, right? So put a little line, and this is 0.14. Always put areas up here and z-scores down here, because they look like each other. So the math is hard enough already. Be nice to yourself. So I know it's got to be way down here, because I want just 14% in there. So it's got to have a little tiny area. Little tiny area. And you guys can figure out the z-score, which will not be the answer yet. But it's got to be part of this problem, is figuring out that z-score. Poor little camera. So again, fight the urge to look up 0.14 here, because that is not a z-score, that is an area. And I know the z-score should be negative, it's below the mean, right? So look at the negative side, find 0.14 in here. And another mistake I see is people do this. There's 0.14, there, no, that's 0.0014, I want 0.14. So it'll be down here somewhere, right? Here's the 0.1s. Where's 0.14? There's a history test right there, 1492. Yeah, you can get pretty damn close to 0.14, right?
What's 1492?
1492?
Yeah.
You don't know? Okay, well, it's not history class, I guess I'll let it go.
I haven't done it.
Anybody know what happened in 1492?
London burned down.
Okay, this is interesting. That's when Columbus discovered America, that's what he started the genocide of American Indians, but we're not gonna go into that. Okay.
Alright.
Yeah, we're not gonna, sorry, I didn't mean to. So that's not the right answer, 1492, I want 14. The closest I get to 14 looks to be this guy, right?
There's another one.
There's another one?
I'm not sure. Negative 2.20.
2.20. Negative 2. Oh, I see. All right, this is perfect. So it's not quite right. We want 0.14, right?
Yeah.
That's 0.014.
Yeah, it's 1
Oh.
percent.
Okay.
Yeah, okay. So 0.14 would be, the closest you get is 0.1401 right there. What z-score is that? It would be negative 1.08. Now that's not the answer yet. Because it would be really weird if I found somebody that it took them negative 1 minute to find a park. What does that mean? Even a minute before they got there, they found a parking spot. Oh, it's there. Right? That's some X-Men level shit, right? Oh, I found it. You know, probably not going to happen, right? You guys with me? So negative time normally doesn't mean much, unless you're going to shoot a rocket off and they got T minus whatever, which means negative time before it lifts off. Anyway, look at this formula here. Let me write it up here again. And let me turn my camera around. This formula is obviously really, really good, but it's really good, this formula here is really good when I know this, and I don't know this. Now, in this problem, can somebody tell me what this represents? Hmm? No. The point 14 is an area, right?
Okay.
What's this here? What's this here for this problem?
The average score.
The average what?
Oh, time.
Mean.
Time. And this would be whatever other time we're interested in, correct? So, like here, why did I put a 53 right there?
Because that's what they wanted to
Because that's the time I was interested in, correct? Okay, so this means some specific time. This formula is good. If I know the time, like 53, I can just put it there and figure out the z-score. What situation am I in? I know the frickin' z-score. I don't know what this shit x is. I'm backwards now, right? I know z, I don't know x. So we just do some algebra. And this was actually on the warm-up sheet, if I remember correctly. Can you take a minute and solve for x, please? Solve that equation for x. Why does this equation suck? What's the worst part of this equation besides it exists?
Division signal.
Yeah, division by this. So you can kill that part, right? So just take a minute. Try to do some algebra to this thing. If I follow his advice, I'm going to multiply by the little fat r dude, little sigma. That immediately makes the formula a lot nicer. And then what's the last thing I have to do to solve for x? Add the mu, right? So I get x is mu plus z sigma. Now, as a student, you sometimes follow along, and you're like, okay, you got a bunch of letters, and you move them around. Good job, Jeff. So I want to show you, really quickly, you guys are going to basically use this formula without directly using it. And I'm going to point it out. So just think about this. If I had a distribution, and I know the mean is 30. Good Lord, Jeff, what is that? The mean is 30. And the standard deviation, let's say, is 12, right? Can anybody tell me, if I go 2 standard deviations up, what is this number? Don't say it out loud. Think about it. If I go 2 steps up, 2 standard deviations from 30 up, what is that number? Don't say it. Try to do it. You can do this. Each step is how big? 12. So if I get 2 steps up, don't say it. I want you to really think about it. A lot of this is simpler than you think. It's just got these weird words kind of thrown in, and the mu and the sigma and bullshit. This is just steps. This is just, this is how big each step is. So what do you get? What is this data point right there? That's 2 steps up. 54. It's 2 of these, right? So you started at the mean, and you went 2 steps up, and every step is 12 big. You started the mean, and you added a z-score times the standard deviation, same damn thing, right? It's the same formula. We did it without even knowing we did it. Same thing happened with probability. We actually did the problem before we even knew the formula for it. So this formula can definitely sit on your formula sheet now. And now I know everything, don't I? Do I know the mean for this problem? Yeah, it's freaking 33.74. Do I know the standard deviation? Yeah, it's 8.63. Do I know the z-score? Yeah, it's negative 1.08. Throw that shit in and do it. I'll stand up here and bounce on my feet for some reason. Do it. You know everything you need now. You know the z-score, negative 1.08, and you've known the mean and the standard deviation for the whole time. Oh. So I'll show you something in a minute. Oh, what's that gonna be, Joe? How would I know? Let's see. Four point three roughly? I don't know. 24.41?
Yeah. Or,
Let's see.
I guess you can round it.
33.74 minus 1.08 times 8.63, 24.42
Yeah.
minutes. I'm a math teacher. I'm also a science teacher, so if you don't put units on something, I'm gonna say, what the shit? Shoes, sheep.
But you're really a science teacher?
Huh?
Are you a science teacher?
Yeah, I've taught physics a few times.
Oh, okay.
Yeah.
Not science.
Math is the most fundamental science, so I could say that and be a true dork. If you're at home, this is what we just did. So it kind of makes sense. I know the answer is going to be less than this because I'm down 1.08 steps. That's what this does. Remind me again, what's the question I'm going to ask you and everything, every test left this semester?
What does the z-score mean?
Yeah, so watch this. What's the z-score tell you? The number of these from the mean to the data point. Right, so it's kind of nifty. Most equations you can kind of read as a sentence. So this actually tells you the definition of a z-score, if you interpret it correctly, right? So I don't let you have notes, but this formula could be a note. Okay, and I love it. Someday I'm going to get more than half of the class answer the what is a z-score correctly. Do you understand what I'm saying? Everybody always is like, tell me what's on the test, and here I'm just telling you exactly what it is, and I don't think maybe once I had more than half the class get it right. I'm like, okay, you guys are going to do it. You're going to be 100%. I know it.
I don't have any question. When is the next test?
Oh, when is it? When is the next test?
Thursday.
Thursday's a quiz.
Yeah.
I think it's a week from this Thursday, if I remember correctly.
I didn't say
That's
this.
so short.
That's crazy. Well, my calculus class, I'm giving them a test tomorrow. Because I'm a jackass. But at least I didn't give it to them on Monday. That would have been like next tier shit. Yes.
I have a question about being a science and math teacher. I've had science teachers talk shit about math, saying that science is just math with a purpose.
Well, what it truly is science could do nothing without math. So, yeah. So, I mean, in one sense, they're right. Like physics, I love it because it's math you can touch. Sometimes you don't want to touch it because then you'll die. But very often it's math you can touch. But yeah, anyway, let's not get into that. That's the old Jets versus Sharks or something from West Side Story. All right, so the last thing I want to do is kind of step into the next idea. We're going to leave a little bit early because I have to go to some classes and do a little presentation, so that's going to be fun. So this next idea is kind of tricky. I will tell you this. All right. There's going to be a lot of derivation of ideas. You understand what I'm saying? So there's going to be a lot of stuff up here that I'm going to talk about and show you that you're never going to have to do yourself, because I'm just trying to get to the point where we can see what a formula is the way it is. The actual math that comes out of this is very minimal, but it feels, the concept is kind of like, whoa, okay. So don't say that to make you feel weird. Just as you listen, realize this is not going to interpolate into like this huge math problem. It's going to be very minimal mathematical changes. The concept is kind of heavy, right? Okay, Jeff, you scared the shit out of him. Okay, so so this is a standard kind of example I've done, and I just can't get away from it, but I kind of like it. Let's pretend we're in some other universe. We're not in C-137. We're in some other universe where Florida, the population of Florida, looks like this in terms of ages. So what the shit does that mean, Jeff? What does that mean? That means
No one's alive at the age of 30.
that there's nobody that's aged, I don't know, let's say, what do you want to say, Jeff? 30 to 60, sure, I don't know, roughly, right? Scale doesn't really matter here too much, but, right? So this is obviously not what our Florida looks like. This is some weird middle Logan's Run thing happening, if anybody gets that reference. So, is everybody with me? So there's a lot of people that are like in their 80s. Do you see that? They go to Florida to retire, play some shuffleboard, turn the heat way up too much, right? And you shouldn't say too much, Jeff. You're getting closer now. And then there's a lot of people, the younger people that are down there, surfing and doing all this kind of shit, yes? But there's not anybody, not just not a lot, there's nobody in the middle for some reason. Is everybody with me? That's a very weird distribution, correct? Okay. So, this picture, how would this picture be constructed if it was a real picture? I would walk around Florida and I would ask people, how old are you? So they would say, I'm 79, so I'm 79. Somebody else said, I'm 1. Okay, there's 1, right? And I would just keep building. So if I had a bunch of, this is how many 1-year-olds I had answer me, right? So remember histograms where the height of the bar was related to the number that was in there? That's really what this is. Is everybody with me? So I constructed this picture by asking individual people how old they were. Now let's say the mean, what's it look like? The mean is going to be 45 or something, let's say, right? Okay, so this is exciting. So this is just kind of like a huge, I have a ton of little tiny rectangles. So this is just one kind of crazy big ass histogram. Because Florida has a kind of a large population. Are you guys all kind of with me? So if I pick one person, what's the most likely age? Would be like either 80 or like, I don't know, looks to be like 18 or something. You guys see that? One of those two, because that's the two peaks. This is bimodal, just to bring that back. Is everybody with me? This weird ass alternate universe Florida, right? So what if I take, instead of asking one person at a time, this is a sample of 1. And by the way, real quick, so I get a mean of 45, and I get some standard deviation. I don't know what it would be here. Okay. If I instead ask, let's say 20 people at a time, I really want this to make sense. So instead of going to each individual person and saying, how old are you, and then plotting the point, I take 20 people and I say, figure out your average age. So I'm not plotting individual ages. I'm plotting averages of 20 people at a time. So if I take every possible group of 20 people, do you understand what I'm saying? That would take a lot of time, yes? Go to Florida. Well, asking each person would take a lot of time. And I take every possible group of 20. Every possible group of 20, and I plot their average age. What would the picture look like now? So we don't know exactly, but we can make a really good guess. Can anyone tell me, if I take a group of 20 people, what's the most likely average for that group?
Most likely average is gonna be 45?
Yes. Is anyone 45 years old?
No.
But, so to kind of more illustrate what you just said, what's the most likely thing? Is it very likely that I pick 20 people at random and they all are right there?
No.
Is that likely? No. What's the most likely thing to happen would be some from here and some from here. So shouldn't they average to be the actual mean? Will that happen with every sample? Is it possible I randomly select a sample and they are all under 4 or something weird?
Yes.
Right?
Very.
Very unlikely, but possible. So what would this picture look like then?
It would.
So there should be a really big peak at 45 now. Because that's kind of like the most likely. What's the next likely thing to happen would be either a bunch of people from here or a bunch of people from here. So there should probably be a little bump at 18, maybe not that big. It doesn't matter, Jeff. And a little bump at 80. Doesn't dry it. Okay, there we go. And then probably falls up pretty quickly. Wow. I love you guys. I really, and again, you're not going to have any math to do with this kind of weird concept. Just does the idea make sense? If I take one person at Grossmont, what's the probability that their age is the average age of Grossmont? Not very big. If I take 100 people randomly, shouldn't their average age be really close to the actual average? I mean, I should kind of randomly get older, younger people. They should all average out, correct? So it should be a much higher probability that the average of a group of 20 people is the actual average.
I would have thought that would have been bell curve.
Not quite yet.
Not yet. Or
Possibly.
Or is it just you need a bigger group?
You do. And the magic number, and actually I kind of pronounce these a little more than they probably would be, to be honest. That's why I kind of shaded it down. I'm like, nah, don't know. If you hit more than 30, so let's say we do 35. If you do more than a sample of 30, and I plot out their averages, then it'll be kind of like this. Is that roughly normal?
Very roughly.
Very roughly. Well, let me kind of, I don't want to make it too perfect, but it should be approximately normal. Let me do that. There's a little bit of a wobble, right? So this is definitely approximately normal. Was the original distribution normal?
Very not.
Very not. It becomes normal enough. I'm going to say normal enough a lot. Remind me, why is it so important to know that something we're working with is normally distributed?
Because then you can apply z-scores and all that.
Because then I can use freaking chart of all the freaking answers, right? This has all the answers on it. When can I use this, Jeff? When I'm working with a normal distribution, right? All right, I love it. I love it. Now, real quick, can you guys tell me this? Whatever the standard deviation is, does it get bigger or smaller for this picture? What does standard deviation tell you?
How far away it is from the...
How far the data points get from the mean, correct? So are there any data points in this original one close to the mean?
No.
Are there any data points in this new one close to the mean? In fact, most of them are close to the mean, correct? So will the spread be more or less? The spread here should be much less. All right, so this new sigma, in fact, I'm going to call it this. I'm going to get you guys, again, to remind me, this was plotting individual people, yes? This was plotting what again? 20. In fact, what exactly am I plotting? I talk to 20 people and I get their average. And isn't that a group, a sample that I take? A sample of 20 and I get their average, right? And then I plot it. And then I go to the next group and I plot it. And I start to question my life. What am I doing in Florida? But this new one, the spread, let me see if you guys are cool with this, of the sample means. The spread of the sample means is going to be less than the original spread. Because now it's all, isn't everything gotten closer to the middle? So what do you think about this one now? This one's gonna be even less. Because now there's even more close to the middle. Okay. So if I kept taking larger and larger samples, what do you think is going to happen to this picture?
More and more closely fit over.
Yeah, if I take the entire population, it of course is going to look, like that. But anyway, yeah. So standard deviation is going to get smaller and smaller, but the mean is going to stay the same. Yes?
Is the sample of 30 the minimum required for it to be approximately normal?
Greater than
or
30.
Is that the closest that you want it to be? Like, because
No, a sample of 1,000 is much better than a sample of 70. But it's got to be greater than 30 to have a distribution that's normal enough.
Okay. But isn't that what's like the upper cap for that? Is it like it has to be that? It has to be more than 30, but it can't be more than like 5% of the total? Or whatever?
Oh, there's something about the 5%. We're not quite there yet. But there's a 5% rule that comes in, but it has to do with percentages. Probably P and Q kind of stuff. We'll get to there. But I want to say this real quick. Let me see. If I have a distribution that starts off looking really gross, I have to have above 30. If I have a distribution that is already normal to begin with, do I need to take a sample of 30 to make it become normal? No. So the nicer the distribution is to begin with, the lower the number can be. But to be safe, we just say it's got to be greater than 30. How did they figure that shit out? They did computer simulations, and they figured out that about above 30, no matter what the distribution started off looking like, it became normal enough, right? So it's just to cover our ass. Okay, so, yeah, okay, we'll try. So the mean, I really want this to make sense too. If I did the average age right now, I get a number, correct? The average age of everybody in this room. I just took everybody's age and took our averages, I get a number, correct? What if I took two at a time and got their average, two more average, two more average, two more average, two more average, and then averaged those? Would it be different? If I take each individual person and take your average, your age, and average those, would it be different if I took two people, averaged, and then averaged all those averages? Would it be different? Is there some reason it would suddenly become older? Would all of us become older or younger if I had two people? No. It would have to be the same average, correct? You guys follow? Okay. That's why the mean, no matter how big the sample is, stays the same. The standard deviation, here's the formula for it, is the original standard deviation divided by the square root of n. So do you see how as n gets bigger, isn't this thing going to get smaller and smaller and smaller? As n gets bigger, I'm dividing by more, so I'm getting smaller, and that exactly matches with what we predicted. Why is it exactly the square root of n? Take some higher math and then come back to me. Yeah. But at least it makes sense. It is supposed to kind of get smaller as our sample gets bigger. And one thing I want you to realize is, if I look at the variance, then it's a little more straightforward. The variance becomes the old variance divided by the sample size, right? So the square root is there because I take a square root for the standard deviation, correct? So that level maybe makes a little more sense now. Okay. So I have my most colorful, which means I have two colors on handout. So I wanted to give you, we've talked about freaking alternate universe Florida. So I kind of want to give you a concrete example. So this will be the last thing we go over, and then we're going to head out. just to give some of you guys dozing off a little light at the end of the tunnel. Okay. So, this is, I desperately want you to understand, this is a difficult kind of idea, but let's see if this makes some sense. So if I put the numbers 1, 2, 3, 4 in a hat, bless you, and then I ask somebody to pick one out, the probability they get any of those numbers would be 1 out of 4. Is that cool? That would be a uniform distribution, correct? There's no reason that 2 should be more likely to be picked, correct? So I write 1, 2, 3, 4 in pieces of paper, put them in a hat, reach it in. There's no reason any of them should happen more than any other, so they're all a 1/4 probability. Is this normally distributed?
No.
Hell no. Should be bigger in the middle, right? Okay. Here's the next P of X. The probability of 1 is 1/4, 0.25, so forth. If I do, remember how you do X times P of X and blah, blah, blah? So if I do that for this, I get a mean of 2.5 and the standard deviation of 1.118. So again, just to remind you guys, this is going to be in the quiz on Thursday. You would do the X times P of X, 0.25, 0.5, 0.75, 1. If I add all these up, I get 2.5. Then I would do X squared P of X, blah, 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 and then I'd use that formula that we talked about before from chapter 4. Does this sound familiar at all? So I just kind of did the work for us. So the standard deviation comes out to be 1.118 for this. Okay. So that's if I take one thing at a time, that's what happens. That's like the first picture in Florida. I took one person at a time and I got a distribution. What if I instead take all samples of size 2? What the shit does that mean? So I'm going to reach in, take a number, drop it back in, reach in, get another number, and then take the average of those two numbers. Just like we were taking people from Florida, taking the average of 20 people, right? Now, why did I make it 2? Because can you imagine how big this would get if I made it 20? It would be 1, 1, 1, 1, 1, 1, 1, 1, 1, and 20. Holy crap. So do you understand what each of these means? I could get a 1 and then a 1, or a 1 and then a 2, and then 1 and then So originally, the data is 1, 2, 3, 4. Now, the data will be the means. So what is the mean? What's the sample mean if my sample is 1, 1? What's the mean of that? What's the average of 1 and 1?
1.
1. What's the average of 1 and 2?
1.5.
1 and 3.
2.
1 and 4. Follow the pattern, you get there, right? So just like in Florida, when I took a group of 20, I then took their averages, and that was my new data. Here, I take every group of 2, I get their averages, that's my new data. So the average of 2 and 1 is 1.5. This will be 2, 2.5, 3. The average of 3 and 1 is 2. 2.5, 3, 3.5. The average of 4 and 1 is 2.5, 3, 3.5, 4. If you don't trust me, you can kind of do the averages, but yeah, once you see the pattern, it's kind of nice. What is the most likely average to get? Doesn't it happen 4 times, right?
4 out of 16.
4 out of 16, I love it. So there's that. This would be, where'd it go? 4 out of 16 is 0.25. What's the least likely? What's one of the least likely averages to get? 1 and 4, because there's only one way to get each one of those. So that's why this is 1 out of 16, and this is 1 out of 16. Do you guys follow what's happening? So to get an average of 1.5, that happens twice. That's 2 out of 16, so that's 0.125. If I plot those, does that picture look roughly normal now? Yes. And this is just from a sample of 2. I didn't get anywhere close to 30. Why did it look normal so quickly? Because was the original distribution ugly? The original distribution is already symmetric, yes? I really want this to make sense. So the 30 number is to cover your ass for any weird looking distribution. But if it starts nice, it should look roughly normal quicker. Because it's already kind of nice to start with. So, if you do x p of x and x squared p of x and calculate the mean of the standard deviation, you get a mean of 2.5 still. Same as it was before. But the standard deviation you get is 0.791. And you're like, oh my God, 0.791. The reason that's important is, what was the sample size again for this?
Sample size is 2.
Yeah, sample size was 2, yes? I took 2 each time. So wouldn't it be the old standard deviation divided by the square root of 2?
Yeah.
So if I take 1.18 divided by the square root of 2, I do get 0.79 freaking 1. So I really want you to understand. Okay, so what's the purpose of this? This is what one of the simplest possible concrete examples look like. Do you understand that if I just made it, instead of samples of 2, if I made it samples of 3, do you understand how big this would get? Because then I have 1, 1, 1, 1, 1, 2, 1, 1, 3, 1, 1, 4, 1, 2, 1, 1, 2, 2, 1, 1, 6. Yes? Maybe? Is that cool? And why is this 16? Because there's 4 options for this, 4 options for that. 16. So what would it be if I did samples of 3? 4 options, 4 options, 4 options. 64. There would be 64 elements in that. Do you want to do that? So thank the gods of mathematics that I have a freaking shortcut. I don't have to get this from actually getting all these numbers. I could just get it from taking the original standard deviation divided by the square root. I don't have to do all this work. So I want to show you one example of what it would look like if I did all the work. And then I want you to see, you get the same number as you do if you just use this formula. So, shoot, real quick, last thing, and then I got to really run. So if I had a situation where the mean is 11 and the standard deviation is, what do you got, Jeff? 4.2. And I take a sample of 40. Will the means be normally distributed approximately? Or normal enough? Will the means be normal enough? What's the magic number? It's got to be greater than 30. So this is greater than 30. Normal enough.
But if it's equal to 30, it's not normal enough.
Exactly.
More than that.
Not officially, yeah. What would the new standard deviation be? The standard deviation for the means. It's going to be the original standard deviation divided by the square root of what? N, 40. So then you just have to do that. You don't have to do all this work, thank the gods, right? I don't want to take samples of size 40 and make that table. That would be so stupid big. I don't want to do that. So this is a little shortcut. So you know, whatever the hell that is.
Yeah. Is that like 2 rad 10?
Say again?
Is that 2 rad 10?
2 rad 10, sure, yeah.
I do not
So
remember.
2.1 divided by rad 10 is 2.1 divided by 3. It's roughly 0.67 something, yeah. All right, guys. All right, that's plenty. So don't forget Thursday quiz, chapter 4 and 5. Then we just got into chapter 7, just to let you know. This is chapter 7. So next time we'll firm up chapter 7. We'll do some more